It's with a real sense of kind of a bittersweet feeling that I'm here tonight. I have a number of friends in the audience that I've known for a very, very long time. Charlie Metcalf, obviously. Jack Hudson, we go back to Edwards days. Robbie Robinson, we go back to Edwards days. Mark Lewis, University of Maryland. And that's the ones I can see because of my eyesight. But it's nostalgic, I think, in some other respects, because this is probably my last official Air Force presentation. I'll be retiring very, very shortly from the Air Force, at least in the federal government side of things. And looking back over time, I've been incredibly impressed with this service and its people and its contributions to national security and its contributions to the United States as a whole. If you take a look at the challenges and problems that this country faces, if there was an Air Force attitude motivating the rest of the population, we'd be doing just fine, thank you very much. And if the United States Air Force could run the world, it would be a better world. So United States Air Force uber alles. If I was Army, I'd say hoo-ah, but that would probably be considered disloyal. I've always been fascinated by the interplay of technology and aeronautics because aeronautics is inherently technological. You know, if you're in the Army, you can walk around and stop moving, and you're not going to fall through the earth. If you're in the Navy and you're on a boat, basically you can stop what you're doing. Unless there's a hole in the boat, you're not going to have a problem with it. But in the Air Force, if you're flying, and you're flying some sort of inferior machine that can't maintain itself in the air, you're in a very, very serious bit of trouble. The Air Force as a service has been a service that's been innately built around technology, and as a result, the Air Force has had a profoundly influential role to play in the development of aeronautical technology, going all the way back to the very earliest days. So I thought that in this swan song presentation, if you will, I thought what I'd do is give you a few thoughts looking at the Air Force and its contributions to aerospace technology. And I'd like to key on three of those to basically focus our discussion. So the first thing I'd like to mention is that if we take a look at the Air Force and technology, we find these contributions across the entire span of flight. Certainly, since the time of the Wright brothers and the invention of the airplane in the 20th century, from the creation of an Army Air Service onwards, looking at the predecessor organizations of the Air Force, we find that there's been a very strong Air Force input to the development of aerospace technology. It covers virtually all technical disciplines involved in flight. The classic ones we think of: aerodynamics, structures, propulsion, controls. If we just use those four as the measuring device, you find significant Air Force contributions in all of those. And it covers all types of operations, whether one is talking about combat operations, commercial operations, humanitarian, military, whatever it is you're looking at, fixed wing, rotary wing, lighter than air, there's an Air Force component to it. So obviously the scope of our talk could be very, very broad indeed. And so for that reason, I've decided to focus on just a few, and I've decided to look at these with the idea that past truly is prologue. And I'll just give one little introductory example of that. If we take a look in the collections of the museum here, we see a very nice reproduction of the Kettering Bug, a cruise missile developed in the World War I time frame, and you can see the direct legacy of that in the advanced stealthy cruise missile of the late 1980s, early 1990s, the AGM-129. Very different capabilities, very different weapons payload, very different ability to actually influence an enemy or have a decisive military effect. But if you think about it, it really reflects at heart what air power is all about. And air power basically is about three things. It's built around speed, and it's built around reach, and it's built around height. Height gives you view gives you awareness gives you the ability to undertake informed decision-making. Reach gives you the ability to hold the opponent hostage at a distance. If we think about David versus Goliath, David didn't grapple with Goliath. He hit him with an aerospace weapon. He hit him with a rock. It was an unguided missile, but, shrewdly aimed. If we think of the British Bowman at Cressy, they didn't wait for the French knights to ride them down. They hit them with an aerospace weapon at a distance. And, if we think about speed, speed gives us that ability to capitalize upon the turn of events, to take advantage of circumstances and turn this to military advantage very, very quickly. And those are the three qualities that really play in all of military history, but are innate, particularly in military aviation. If you take a look at mobility, and I'll get to this much later on in my talk, it's very interesting to me that if we take a look at relative rates of mobility, we entered the 19th century at 6 miles an hour, the speed of a horse-drawn vehicle. We entered the 20th century at 60 miles an hour, the speed of a steam locomotive, what might be termed strategic mobility. And then we entered the 21st century at 600 miles per hour, the speed of an air transport system, a jet airliner, because, you know, if we take a look at these normative forms of transportation and mobility, we see here, I think, really the transformation that you have when you get away from the surface, when you start operating in that air and aerospace environment. You're able to capitalize on technology, you're able to capitalize on the qualities of speed and maneuver much better than you are when you're constrained by moving in a two-dimensional surface type of construct. And that's why if we look overall at military power and projection, we find a very interesting thing. We find that by the middle of the Second World War, we're seeing a change in the paradigm of war. We're seeing that no longer is war decided largely on the basis of two-dimensional surface movement. Indeed, we're finding that those forms of warfare are increasingly archaic. To give two examples, if we look at naval combat, we find that by the middle of the Second World War, just looking at the Japanese fleet, we find that 48% of the Japanese fleet is sunk by submarines, 45% is sunk by airplanes. In other words, the two great three-dimensional systems that were developed in mechanized warfare in the 20th century, the submarine and the airplane, have radically transformed, changed, and indeed ended a heritage of military combat going back thousands of years. If we take a look at surface warfare, Dr. Siegfried Handlöser, who was a lieutenant general in the German military, a rather repulsive character actually, who was in charge of determining the medical requirements for the Third Reich, he takes a look at the military casualties that he's confronting. Not the casualties from the city bombing, nothing involving civilians here, but just looking at the combat casualties. And he finds that by the middle of the Second World War, the majority of his casualties from all fighting fronts are caused by Allied air attack, and secondarily by artillery, and then thirdly by everything else. In other words, the weapons with the greatest reach. And this cuts to the heart of a matter that was first enunciated in 1945 by Major General J.F.C. Fuller of the British Army, when he said that if you looked at military history at any particular point in time, you had to build your fulcrum of combined tactics, as he termed it, around the weapon with the greatest reach. And he said that in the era of the airplane, that weapon is the airplane. Now, here's an individual who was one of the pioneers in thinking of what we would call armored warfare, or in the German sense, blitzkrieg warfare. But it shows that this fellow was no dinosaur. He may have been coming out of that ground warfare community, but he definitely had an air and a mobility focus there. So with that in mind, let us take our trip down memory lane and take a look at some of these developments. I'd like to concentrate on three areas of technology where I think Air Force investment in science and technology made a significant input, and that is the invention of the so-called modern airplane in the 1930s, the jet and supersonic breakthrough of the 1940s and the 1950s, and then hypersonics. The last is a revolution as yet unfinished, but one that I think is most worthy of our attention. And I would like to point out that since I'm dealing with the gospel of air power, I might as well mention a couple of visible saints. And one of these is, first and foremost, General Billy Mitchell. General Mitchell, at whom I genuflect every time I mention the name. Billy Mitchell is far more than about sinking battleships, as laudable as that was. Billy Mitchell was also about creating the kind of science and technology establishment that we have in the Air Force today, and indeed about the kind of federal establishment for aeronautical research and development and aeronautical operation that we have today. He wanted to create a national aeronautical agency. When you take a look at what he was trying to accomplish, he was trying to accomplish something akin to a combination of NASA and the FAA. He was using as a model the British Air Ministry. On top of this, he wanted to robustly support aeronautical research and development. He wanted to create a National Air Academy. This was more than something that was just equivalent to what we would consider the Air Force Academy today. He wanted an academy that would address both civilian and military aeronautics as well, because he really felt that the future for this nation was a future that was built around air travel and built around military power projection through the air. Because of this, he was extremely enthusiastic about supporting Air Force investment in science and technology, research, development, test, and evaluation, and we are his heirs. Everything we do stems directly from this man. The second individual I would point to is Hap Arnold. If Mitchell had the vision, if he was the John the Baptist figure, well, I won't say who Hap Arnold was, but you all get the view. Hap Arnold was the man that, although he avoided being crucified, came very close several times, was nevertheless the individual who really made this all happen. Hap Arnold had his career nearly destroyed after the Mitchell court-martial. He was consigned to oblivion, but he stayed in there, even though he was tempted to join the commercial world. He stayed in there, hung in there, and then, of course, became our air leader during the Second World War. Arnold was an operator. He was an operator in the sense that he always had an operational focus, but he also had a shrewd appreciation for how to apply science and technology to military need. And he was very astute in trying to seek high-quality science and technology advice. And in this, he was greatly aided by the third of our visual saints, and that is Theodore von Karman. Theodore von Karman is a fascinating individual. We all hear the name. Here's a quick song and dance about him. His father, Maurice von Karman, actually Maurice Karman, had reshaped the educational system of the Austro-Hungarian Empire. And he had done such a fine job at this that Franz Josef, the Austro-Hungarian emperor, had given him a noble title, had made him a Von. Franz Josef, in retrospect, you know, we look at him historically, he's a pretty sympathetic guy, actually. I think he was a pretty decent human being. In any case, von Karman came to this country at the end of the 1920s because, being Jewish and being a smart man, he realized there was not much of a future hanging around Germany at that point. And he wrote a memorable letter to the German Ministry of Education when they requested he come back, and they said, if you don't come back, we'll fire you immediately. He said, I hope you will do as much for German education and engineering over the next 10 years as you have done for American education this afternoon. Well said, actually. Theodore von Karman may have had a huge ego, but by God, the guy had class, and he was justified. Theodore von Karman, of course, headed the Guggenheim School at the California Institute of Technology. I say that with some apology towards Mark Lewis, the Air Force chief scientist, because he's an MIT grad, but that at least was another Guggenheim School. I'm sorry, Mark, I have to mention Caltech. I'm sorry, it's just there. But anyway, to make a long story short, von Karman developed a very close association with Hap Arnold. And when Hap Arnold went to England in 1941 and was exposed to the development of the jet engine, he realized that we had really in many ways missed the boat. And he wanted to make certain that this never happened again. And so from that point on, he relied extensively on Theodore von Karman, used Theodore von Karman as essentially his chief scientist, to put it in modern terms, had von Karman undertake a very influential study of science and technology in the Air Force at the end of the Second World War, and then out of that came the creation of the Air Force Scientific Advisory Board and the position of Air Force Chief Scientist, which we have to the present day. Theodore von Karman transferred in very large measure European aeronautical education practice to the United States in conjunction with another emigre, a Jewish emigre from Germany, Dr. Max Munk, who went to the Catholic University of America after working with the National Advisory Committee for Aeronautics. These two individuals really gave to the United States European-rooted, experimentally rooted aerodynamics, which radically transformed the way that we approached the design of the airplane in the 1920s and the 1930s, and they really start the ball rolling on where we subsequently go in science and technology. The other thing I'd like to point out, and not simply because I'm lecturing here in the Miami Valley, is that we are really heirs of what I call the McCook-Wright Field legacy. if you take a look at the Air Force and its predecessor organizations and what we gave to aeronautical design and technology, basically these subject areas are what we gave to it. We had come out of the First World War deficient behind the European nations in both the science and technology of flight and in the practical operational skills of flight. We had had some notable successful moments in the First World War, for example, with Billy Mitchell functioning very much as the first, if you will, Joint Forces commander of air power forces at the Battle of St. Mihiel, the first JFAC, we might even call him, to put it in those terms. But if we take a look, we were dependent very much on European technology. Our people were flying European-designed airplanes. They were flying SPADs, they were flying Newports, they were flying Brigades, they were flying SE-5s, they were flying Camels. They weren't really flying airplanes, unless you were in the Navy and the Maritime Patrol role. They weren't really flying airplanes manufactured by American manufacturers. So we started out in the 1920s from a position of relative inferiority. And yet, by the 1930s, we rose to the top of the aeronautical profession, certainly in terms of our ability to undertake the development of long-range, high-performance monoplane transport and bomber design. And these were the areas that we really mastered, and these were areas that were uniquely pioneered here. If you take a look, for example, at the work of Virginius Clark in streamlining, Alfred Verville as well, in streamlining and airfoil design. If you take a look at the work of Sanford Moss and S.D. Heron in engine development, engine cooling development, turbocharger development, Frank Caldwell in propeller design. If you take a look at some of the work that came out of Wright Field in the field of structures with people like John Younger and the influence that had on subsequent industry design practice at Boeing and at Northrop, high-altitude flight with Carl Green, the development of the XC-35 research airplane in the 1930s, which gives to us the first practical pressurized cabin. If you take a look, and this is very important, in the development of an engineering school capability here, the AFIT's predecessor, the Army Air Corps Engineering School right here at Wright Field, this was a nurturing and a training ground for people who went on to prominence in industry, in the military, in the academic world, and in the civil service. And this was not something that was innocuous. Engineers like Ezra Kocher, the man, for example, who more than any other single figure is responsible for the development of what eventually becomes the Bell X-1, the first supersonic airplane, right here, an instructor at the engineering school in the 1930s. So these are kind of the things I'd like to talk about and focus our attention on. In the 1920s and 1930s, we had the advent of what we might call the modern airplane. If we think about this in very popular terms, at the beginning of the 1920s, the airplane was basically a biplane. It was externally braced, open cockpit, fixed landing gear, thin airfoils, very high drag, relatively unreliable, relatively poor cooling. Aside from that, it was a great development. Now, by the end of the 1930s, we're dealing with an all-metal airplane. It's internally braced, it's streamlined, enclosed cockpit, enclosed cabin, carries reasonable payload, has up to a 200-mile-per-hour cruising speed, retractable landing gear, controllable pitch propellers. The engines are enclosed in cowlings that are fixed on the cells at the head of the wing, at the leading edge of the wing, so that you have a smooth aerodynamic design here, minimum airflow, et cetera, et cetera. How does this all come about? It comes about largely in many ways through the kind of things that we see taking place here at Wright Field in the 1920s and the 1930s. Now, the progression of aviation technology is never really smooth, and it has always been characterized by its share of discontinuities and difficulties. And so there's not necessarily a straight line from, to use the word, technology demonstrator to final product that we would like to see. I particularly don't like this word technology demonstrator. I'm not alone in this. There's a lot of other people, once again, notably Dr. Lewis, who's unhappy with this term as well. Demonstration is something you do in science class in college or high school. If you can demonstrate something, you're not really learning anything from it. Okay? Technology exploitation, technology verification, that might be perhaps a better term. We had people that early on tried to incorporate advanced aeronautic developments and create what we would consider the modern airplane. And that's why you see this tubby little airplane, the Dayton Wright Racer, that you have in the corner of this slide. By the way, this aircraft still exists. If you go up to the Henry Ford Museum in Detroit, it's there. And I would strongly urge you to see it. It's a very interesting machine to see because it incorporates a number of interesting devices. It incorporates a camber changing mechanism on both the leading and trailing edge. So you have camber changing ability with deflected leading edge, what might be called a leading edge flap. It's not a slat or a slot. And then a trailing edge flap as well. You have a retractable landing gear. You have a relatively streamlined monocoque or shell fuselage here. The only problem this airplane really had was really kind of an awkward aerodynamic design. And that was in part to the engine it had. It had a Hall-Scott engine with an awkwardly placed radiator. So you have this weird sort of blunt wall front end effect here in this design. But otherwise, it was an aircraft that really indicated that the future of aircraft design would probably be a future that was based upon streamlining airplanes and going toward cantilever monoplane structures where you were using lift-enhancing devices that would enable you to design smaller wings, therefore wings that had less of a drag loading and could give you a higher performance. If we think about how this philosophy emerges, we see it, I think, placed very well in the development of the Boeing monomail aircraft by the end of the 1920s. Now, I could have thrown in Jack Northrop's Northrop Alpha, which was a very influential and intriguing airplane at the same time period. But I chose the Boeing monomail because this was actually rooted in the structures work that came out of Wright Field and rooted out of the aerodynamic work that came out of Wright Field as well. This aircraft still has some of the hallmarks of older aircraft design. Initially, it's a fixed-wing machine. You have an open cockpit for the pilot. You have an enclosed cabin for the passengers. It has some of the elements here that we see in Northrop. You have an exposed engine. It's not yet cowled. Eventually, it will be a cowled engine to improve cooling and reduce drag. Boeing finally gets its act together, if you will, somewhat gets its act together, with the aircraft that you see down in the lower corner here, the Boeing 247 of 1933. This aircraft is the first modern twin-engine, all-metal transport that this country develops. It's a very significant airplane. It is not a perfect airplane. It has a lot of attributes that we would consider less desirable by the standards of later aircraft design. And that's why Douglas was able to capitalize on transforming it and making it what it could have been, if you will, with their DC-1, which was placed in production in slightly larger, more powerful form as the DC-2. But the point here is that over the 1920s and into the 1930s, by the blend of aerodynamics and structures research largely pioneered here at Wright Field and by the United States military, we were at a point where we were set to dominate the development of long-range air transport design in a way that could not be foreseen by the Europeans. The Europeans at this time, and I think it's largely because we were dealing with basically non-democratic class-rooted states, the Europeans were building a model of air transport based upon elites. They were not concerned about flying large numbers of people with high speed to achieve great things. They were concerned about flying fewer, smaller numbers of people in opulent luxury around various empires, and as a result, the aircraft design they came up with was relatively awkward. We think, for example, of the awkward biplanes of Imperial Airways of the 1930s, aircraft that were hopelessly archaic by the end of the 1930s. Now, what this gave the United States, to put it in modern terms, was a dual-use industrial base. We wound up having a base that could be applied both to military and civil need, both for commercial air transport and then for the development of the military capabilities that we saw in the Second World War. And encouraged in the 1920s by the air racing experience, but then as well by incorporating these developments and applying them toward the design of high-speed airplanes, we had the makings of what would be the air superiority fighters of the Second World War, and I'm thinking largely because of the convenience of pointing the technology through one particular form of technology, the radial piston engine fighter. I think it's very interesting to take a look at these three aircraft here. You start out at the end of the 1920s with a classic compromise airplane, if you will, the Boeing P-26, externally braced wing, fixed landing gear, open cockpit. Nevertheless, it's a monoplane design. The radial engine is incorporated in what we call a town-end ring. It's not a very effective cowling, but it works better than nothing at all. We see here some of the hallmarks of modern aircraft design. By the middle 1930s, we have now the Curtiss P-36. We have here an aircraft that is much more streamlined, enclosed cockpit, truly a cantilever aircraft. It has a retractable landing gear. Not necessarily the best design in the world, but it works okay. The aircraft is optimized for air combat, obviously has the potential for years, not merely months of service. And then finally, when we get up to the 1940s, we're at the point where we can contemplate the development of something such as the P-47, which is a fully capable, extremely high-performance, successful multi-mission aircraft that really represents, if you will, the zenith of fighter aircraft development in the piston engine propeller-driven era. An aircraft that can be applied to dual-role missions, air-to-air, air-to-surface. It's turbocharged, can get you up to 40,000 feet, 420-mile-an-hour top-end speed, 850 caliber machine guns, 4,000-pound weapons capability, 2,000-pound bomb on each rail outside the landing gear. I mean, we're dealing here with a pretty comprehensive machine, the kind of thing that gave the Germans nightmares in the post-D-Day timeframe. Beyond this, the educational base we saw with organizations within the United States, the Guggenheim schools, which were set up around the country, particularly the Air Corps Engineering School here at Wright Field, the capabilities that we saw emergent in our industry, the Northrop influence, which was pervasive because of his influence among many different companies, we started to build an industrial base so that even though money was not terribly available, and even though we were building things in small numbers, take a look, for example, at this A-17 production line from the middle 1920s. It almost has this, nostalgic feel of a hobby shop craftsman-type operation. This was setting the stage for what we had in World War II. Just shy of 300,000 airplanes manufactured by the United States. That's over twice as many as Germany and Japan together were able to produce. And we were able to produce not only for ourselves, but as well for our allies. I show here a production line for B-24s in San Diego, another production line for A-35 dive bombers for the Royal Air Force. This set the stage, really, for what we exemplified in that war. We had total dominance of combat air missions in that war. Whatever combat air mission you were looking at, we owned it. And, it always interests me that when we take a look at the value of air attack, we never have to look at the statements of airmen. All we have to do is look at the statements of our enemies, which are very interesting, and the statements of our friends. When Dwight Eisenhower landed at Normandy, his son said to him, looking around with him at the beachhead covered with material, he said, if you didn't have air superiority, you'd never get away with this. And Eisenhower said, if I didn't have air supremacy, I wouldn't be here. He recognized he had something that went well beyond mere superiority. And when you take a look at Joseph Goebbels, once again, one of the most odious figures in human history, when he writes, shortly before committing a squalid suicide in 1945, the cause of all our problems, the Fuhrer and I are agreed, is Allied air superiority, that's a tribute to Wright Field. So there. Anyway, moving right along. You can see I kind of believe in this stuff. Anyway, moving right along. The second case I'd like to talk about, because it's a complex case, is the arrival of the jet age. It's important because, once again, even though we had done all these things right in so many other ways, even though we were masters of the development of the conventional airplane, it showed what happens when you don't keep your focus further enough in the future. You had the first flight of a turbojet airplane by the Heinkel 178 in August 1939 using an engine developed by a man named Hans von Ohain. Some of you in the audience may remember Hans von Ohain. He worked here at Wright Field after the war. Treated far better than we would have been treated, say, had Hitler won the war. You have the Gloucester E-2839, which flies in May 1941, which was, of course, a product of Frank Whittle, another centrifugal flowjet engine. You have the Bell XP-59 in 1942, October 1942, which flies on the basis of two Whittle engines, which are built in this country under license by the General Electric Corporation. And then in 1944, we have the appearance of the jet engine in combat, and that's with the Messerschmitt 262. Now, this was an aircraft that could have been profoundly influential had it been introduced into service just a little bit sooner. It was an aircraft that was an ideal bomber-destroyer in terms of the capability of the weapons package it had. 4 30-millimeter machine guns in the nose. But for a variety of reasons, not least of which was doctrinal problems, the Germans never made successful use of this aircraft that they could have, which, for which we can be fortunate. The other thing is its introduction into service coincided with the oil campaign and the transportation campaign that both Bomber Command and 8th Air Force ran, and which absolutely devastated the ability of the Germans to move things around their country and also to supply their organizations with fuel. I was struck by looking at a painting that was done by an artist a few years ago that showed German night fighters in 1945. It was one of these imaginary views of German night fighters, et cetera, and it showed the pilots being delivered to their airplanes by Mercedes automobiles. And I got thinking, in 1945, nobody was driving pilots up to the ramp in a Mercedes automobile. They were trying to find fish oil to fly their airplanes. Anyway, neither here nor there. Our response was this machine here, the Lockheed P-80, developed in very rapid time, 143 days, by Kelly Johnson. I think we've all probably heard the story, the birth of the skunk works, if you will. And it's all true. This is a test variant of the P-80 that was flown by the National Advisory Committee for Aeronautics at Ames Research Center, hence the pitot airspeed boom that you see coming out of the nose. But this was a very nice 550 to 560 mile per hour airplane. It was fully capable of duking it out with the ME-262 and more than holding its own. But it was a case of us being behind. And so the question is, why did we miss the jet? And if you take a look, the reason is really because of these reasons. The United States Air Force, the Army Air Forces as our predecessor, trusted other federal organizations. We trusted the National Advisory Committee for Aeronautics that told us that they knew everything there was to know about science and technology, and that, they didn't think that the jet engine would be a viable product. We trusted the U.S. Navy, and they said, the jet engine might possibly be used to propel boats, but we don't even think it can do that. And then industry was pretty happy with the piston engine propeller combination. It's really interesting to me that if you take a look at Hans von Ohain, who invents the jet engine in Germany, he's a physicist in background. He's not coming out of the aeropropulsion community. And if you look at Frank Whittle in England, he's not coming out of the aeropropulsion community either. He's a test pilot. He just wants to go fast. I mean, that, it's good value. And so when you take a look at this, take a look at the over-reliance we had on the established conventional thinking, and then those fatal words, no defined need. Hey, no customer has come to me and said, build me a jet engine. Hey, nobody told you to build a steam engine either. When you take a look at this, people were just reluctant to go down this road to develop this kind of capability. The other thing I think that hurt us is in the 1920s and 30s, we were blessed by having this tremendous distance from conflict sites, from the war in Asia by the Pacific Ocean, from the war in Europe, the burgeoning wars in Europe by the Atlantic Ocean. We could concentrate on what we really wanted to concentrate on, and that was the long-range transport and the database that might influence the development of long-range bombers. We really weren't thinking about high-speed flight. And when you coupled that with technical misjudgments, for example, looking at duct burning, basically taking a piston engine, driving a ducted fan, injecting fuel, burning it downstream, and passing it through a nozzle, that tended to set the stage where we missed what was actually the critical development of the middle of the turbojet high-speed revolution that took place in the middle of the last century. Now, what I'd like to embark on here is to show how we played catch-up. Well, we played catch-up very, very rapidly. I mentioned Ezra Kocher, a very influential figure who was teaching here in the Air Corps Engineering School, and who then, as a major in the Army Air Forces during the Second World War, was working with the Air Technical Service Command. Ezra Kocher, in 1944, had come up working for General Franklin Carroll with the concept of a so-called .999 research airplane. This was a humorous allusion to the notion of the impenetrable sonic barrier. And this design, which he showed to a chief engineer of Bell Aircraft Corporation in December 1945, Robert Woods, this design really triggered the subsequent development of the Bell X-1. So if we take a look at the supersonic high-speed breakthrough that begins in this time period, and we start to take a look at data points in the progression of things, we have the first Mach 1 flight then, October 14, 1947, by that well-known battery salesman, Chuck Yeager, Mach 1.06, 43,000 feet, 700 miles per hour. We extend this to Mach 2 with the late and great Scott Crossfield, November 20, 1953, Mach 2.01. Just gets there, barely, but there he is. And then we extend that to Mach 3 in 1956. This is a very rapid envelope expansion and development of aircraft design and design capability and demonstration of mastery of aerodynamics over this time. And it does not come without a price. We had serious near misses with the X-1 program, even with the D558 program, and unfortunately we ran out of luck with this particular flight. On September 27, when Mel Abt made this flight, he was killed when the aircraft went out of control through inertial coupling as he turned back to Edwards after completing his high-speed run. The aircraft departed violently, and he was killed in the ensuing instability and attempted flawed ejection. We went to Mach 4 with a ramjet-powered vehicle called the Lockheed X-7, which, if you take a look at the lines of this aircraft and you kind of squint hard and you move that horizontal tail to the top of the fin, you know, you sort of see the F-104, if you will, in the design layout of this vehicle. But basically the point here is that we went through the supersonic era by increasing the Mach number of piloted or high-performance vehicles roughly 1 Mach number every 2.7 years. That's a pretty incredible rate of advance when you think what's happening over the previous years of aircraft development going all the way back to the Wright brothers. Now, if we graph this, you know, I think we kind of see this in graphic form, and, you know, I leave as a teaser out there the hypersonic region, which I'll be getting to shortly. But what we saw that was more significant was the radical transformation, once again, largely driven by military requirement, of aircraft configuration in this time period. In 1935, a German engineer named Adolf Busemann at the Volta Conference on High Speeds in Aviation in Rome had postulated the swept wing as a means of alleviating the drag rise and the shock wave formation that one associated with straight wings as you approach the speed of sound. His paper went largely unnoticed at that time, although the Germans subsequently put a great amount of effort into swept wing development. But it was largely unnoticed by other countries and by other engineers, including, surprisingly enough, von Karman, who was attending in the audience. The rediscovery, if you will, of the swept wing in the rubble of Nazi Germany, and the fact that another American engineer, Robert Jones, had independently discovered it in his own work at Langley Laboratory and then had verified it in wind tunnel tests at Aberdeen Proving Ground, really ginned up a transformation. You know, if we think about it today, when you drive down a highway and you see a sign for an airport, what do you see? You see the symbol of a swept wing airplane. It became iconic. The swept wing airplane became the iconic symbol of aircraft in the world today. Now, what's interesting is we have always had a leader-follower relationship in military and civil aviation. Typically, a development gets demonstrated in the wind tunnel on a technology experimental verification platform of some sort, and then from that point it gets applied to fighters, it gets applied to bombers, it gets applied to transports. And the example I'd give with the swept wing is this classic progression, F-86, B-47, Boeing 707 prototype, the so-called 367-80. This is really, if you will, the progression of the swept wing over roughly an 8-year time period in the United States, where we're going from first fighters to strategic bombers and next to the Boeing 707, which of course was the 367-80 was the genesis of both Boeing transport design and of course the KC-135. If we take a look at how this plays in just one company's products, we tend to see kind of an interesting thing. Here's the P-51, the F-86, and the F-100. And as we see, there's a very small number of years here that take us basically from the 440-mile-an-hour airplane to the roughly 960-mile-an-hour airplane. It's very, very interesting to see how you have changes in fineness ratio. Planes get longer and pointier. You have an increase you have a decrease in aspect ratio on the airplane. You have tremendous decreases in the thickness of the wings. Of course, you have a major change in propulsion. You go from a propeller-driven airplane to the non-augmented jet-powered airplane to the afterburning jet airplane. This just shows, I think, very quickly the kind of changes that we witnessed in this time period. And what this gave to us was really a golden age. You know, we look back, those of us that are supersonic babies, I was born in May 1948. I count myself fortunate among that. You know, we grew up in a time period where we owned the world, you know, frankly. You know, our aircraft was sort of the gold standard whether you were taking a look at military or commercial values. And it reflected really the tremendous competency and capabilities of the aerospace industry, which itself reflected everything that I pointed to before in terms of our wartime industry, the development of the industry in the 1920s and 30s, the whole culture of air-mindedness that we had at that time period. And it could be exemplified by a doctrine that the Air Force enunciated in 1990, which really encapsulated this, and that was the doctrine of global reach, global power, which came out in the summer of 1990. Bombs or bullets, you know, bread, you know, it was your choice, whatever you chose. If you needed us for humanitarian relief, if you affronted the United States and our friends, you know, we could deliver power to help or to hurt you over global distances very, very quickly using the range of capabilities that we had developed. And some of those capabilities were pretty exotic. If you think of Mach 3 sustained cruise as typified by the Blackbird program, if you look at the burgeoning interest we had in winged hypersonics taking us up to the edge of space as well. Now, having said this, once again, it's really interesting to take a look at what we missed, the close calls we had. We were not the first to pioneer any one of these. Even those that we invented, we did not take advantage of pushing them until others did so before us. Now, living on your enemy's mistakes is no way to make your future. But basically, it's kind of interesting to think that if you take a look at things like liquid fuel rockets, Robert Goddard, 1926, first liquid fuel rocket, the Kitty Hawk of rocketry, Auburn, Massachusetts, it's the Germans who produced the V-2. If you take a look at precision air weapons, we take a look at the German use of guided weapons such as the Fritz X on exhibit in this museum in 1943, sinking the battleship Roma. If you take a look at radar, we did a lot of interesting work there in the 1920s, but it was the British that really made it happen. The swept wing, we had the chance to work in this area, but nope, instead it was the Germans that pioneered that. Earth satellites, could have launched one in 1954, but it was the Russians that launched one in 1957. Human presence in space, well, Yuri Gagarin. You know, take a look at all these things. These are rather disturbing tales of how we came close, but nevertheless dropped the ball. The biggest of these was Sputnik, which I remember very, very well as a kid. Now, what I remember from Sputnik, I think is maybe different than many people. My colleagues and I were cognizant of the space race. It may not have been called a space race at that time, but it was. We had our little weekly reader series, and we knew that there was this thing called the International Geophysical Year. Some of you may remember that. And, you know, we knew that the Russians had said that they were going to launch a satellite. And so, you know, I get up on October 4, 1947, and my parents are ashen-faced, and they said, my God, the Russians have launched a satellite. Well, yeah, duh, you know. But it wasn't just our parents. I mean, it was our teachers, too. Our teachers, oh, my God, the Russians launched a satellite. You know, well, pay attention, people. This is how things are changing. It's the way our kids react to computers today. You know, we go in and we think, how the heck are we going to handle this? And the kid goes in and with 3 finger strokes, you know, all of a sudden everything is wonderful again. We fail to keep that appreciation that children and young adults tend to have where they know what's going on in ways, sometimes ways that we wish we did know. And are able to compel us forward toward a future that may not be necessarily the future that we foresee. In the case of the NACA, which was a low-budget federal agency, all of a sudden money hit full force, and that's why I have this cute little sign here of the NACA versus the NASA, which, of course, came out of the National Space Act of 1958. Now, this brings us to our third case study, and in some ways our most interesting because it's a study that's yet to be fulfilled. This is the history of hypersonics in the United States in one kind of weird, mishmash of a slide. I've thrown together a bunch of programs here, aerodynamic programs, some of which were transonic, supersonic programs, some missile programs, some things that were blended wing lifting bodies, blunt body test vehicles, reentry test vehicles, concepts for hypersonic vehicles of various sorts. But the point here really is that if you take a look at hypersonics, to me, hypersonics is a natural blending of the air and space medium. It is where we truly see a confluence of air and space coming together. And I threw in the X-51 here because I knew that Mark Lewis was going to be attending tonight, and I wanted to make him feel good. I'd like you to stand up, Mark, and bow to the audience because thanks to Mark Lewis, we have an X-51. He picked the name. He thought it was really kind of a neat play on the X-15. And DARPA heartily concurred. Anyway, moving right along, we had some sporadic efforts at developing data on hypersonics, largely related to the problem of delivering a nuclear warhead through the atmosphere. A man named H. Julian Allen, working at the Ames Research Center, had come up with the concept of the so-called blunt reentry bodies. Some of you may remember from the 1950s the beautiful space artwork of Chesley Bonestell, where you had very sleek, sharply pointed spacecraft flying in orbit and returning to the Earth and whatnot. Well, you know, if you actually put these suckers in a wind tunnel and you ran hypersonic airflow past them, that nose melted very nicely. Thank you very much. And so H. Julian Allen realized if I develop a blunt body shape here, I have a standoff shock. It carries off about 90% of the heat load of this vehicle, and I can actually get through the atmosphere. And so blunt bodies really became the way to do things. We developed a research vehicle in the United States Air Force, a very important vehicle, not terribly appreciated, called the X-17. It had 4 stages. The three stages would fire you vertically. The 4th stage would turn around and then fire you straight down through the atmosphere, and you'd develop a very high thermal loading on the reentry package, whichever it was, and you could use this to develop all sorts of information about reentry conditions. But once again, this was aimed largely at simply getting some sort of symmetrical blunt body down through the atmosphere. The idea of doing something more intriguing, where you were actually developing a lifting hypersonic reentry body of some form and maneuvering this through the atmosphere, this was a very different issue. The first one here of any significance was the Alpha Draco, which was a McDonnell program. It was a Mach 5 plus vehicle. It achieved the first Mach 5 flight February 16, 1959, a slender cone hypersonic lifting body shape. Moving beyond this, we had, in hypersonics, the development of the X-15 program. Now, the X-15 was, once again, an aircraft that was funded largely with United States Air Force money, a program that was run to a great degree by the NASA at the time that it finally got flying, and which had a Navy component as well. But this was largely, in many ways, an Air Force program run right out of here, the Wright Air Development Center, as it was called in that time period, the so-called WADC. It gave to aeronautics the first Mach 4, 5, and 6 piloted flights. And the first Mach 6 flight was November 9, 1961, by Bob White, very fittingly an Air Force pilot. So once again, we see ourselves starting to turn the corner on this curve, which very rapidly becomes asymptotic. The X-15 ultimately flew 199 research flights. Scott Crossfield would tell you, the late Scott Crossfield, that it actually flew a 200th flight when the engine blew up on the ground when he was testing the engine and flung him forward 75 feet at about 50 Gs. But that, unfortunately, did not qualify for the record books as an official 200th flight. In any case, we have in the collections of the museum here, perhaps in my view, the most interesting of the 2 surviving X-15 vehicles, the X-15A2, which was the vehicle that went to Mach 6.70 in October 1967, piloted by then Major Pete Knight. That aircraft was a remarkable machine. You know, if you take a look at it, we developed a fully redundant system here with a throttleable rocket engine, a flight control system capable of flight in the atmosphere, flight on the fringes of space, a mix of aerodynamic controls and then reaction controls, the little kind of jet thrusters that became much more common on spacecraft afterwards. And it was, to put it within the context of the research aircraft programs of the United States, it was round 2, as it was called, to the supersonic research vehicles, the so-called round 1 vehicles that we had in the 1950s that preceded it. Aircraft like the X-1, 2, 3, 4, 5, the D-5581, the D-5582, and the XF-92A. I feel like I should be doing some sort of a strut up here when I come through all that. But these were seen, round 1 and round 2, were just seen as really predecessors for what was termed a round 3, which never really came about, unfortunately. The first comprehensive study here were some industry studies. One thinks, for example, of brass bell, robo for rocket bomber, industry studies coming out of the Bell Aircraft Corporation in the 1950s. But a very influential study was the hypersonic weapons study that was done by the Air Force in conjunction with the National Advisory Committee for Aeronautics in 1956. The design point for this vehicle here was Mach 15. Those nice little cones that you see on the wingtip are actually not propulsion devices. They're actually aerodynamic control devices. They're basically drag cones to help you control the vehicle during flight. And this one is flying, I use that loosely, in the NACA Langley Memorial Aeronautical Laboratory full-size tunnel. What Highwoods pointed us towards was this particular vehicle here, Dinosaur, the so-called X-20 research vehicle. I feel that we made a very serious mistake in not pursuing the X-20 program. It was a so-called lofted boost glider. It was a flat-bottom hypersonic delta with splayed end-plate vertical fins. You had a tilted ramp on the back end of the vehicle for longitudinal stability at hypersonic speeds. You had a tilted forebody as well. The vehicle had a heat shield that would enable the pilot to have safety and security during reentry, and then would be discarded before landing. This program was about 2.5 years away from his first flight when it was canceled by Robert McNamara. Yet again, one of McNamara's many bad decisions that he made when he was Secretary of Defense. If we take a look at this craft, had we pursued the X-20, we would have developed, I think, a technology base that would have dramatically transformed the way that we approached hypersonics in the subsequent history of the United States. If we go beyond this and we think about its substitute, it was supplanted in favor of a thing called Manned Orbiting Laboratory, which was itself canceled. Had we gone ahead with MOL, the Manned Orbiting Laboratory, the space station that we are seeking to build today would largely have become a fait accompli, because we would have actually achieved this through incremental growth and development. We did neither, and we're paying the price, I would argue, in our national space program to the present day. One of the major values that the X-20 had is that it focused our attention in hypersonics on the facilities shortfalls that we had. This is a chart that I have taken from a textbook in hypersonics that was written by the head of hypersonics research for the Arnold Engineering Development Center at Tullahoma. And it shows you the disparity between the reality of what we could actually achieve in test facilities and the claimed performance that adherents often had often thought. This is very reminiscent, when you look at this chart, this is very reminiscent of the problems we had in wind tunnel design in the 1920s, where you had wildly disparate claims between the reliability of data coming out of a wind tunnel and the matching of that data to the actual performance of flight vehicles in actual flight. And that led to in two directions, to better tunnel development and better analysis of tunnel flow, and then it led as well to the so-called variable density tunnel, which was a very important technical development in the history of aerodynamics and the history of aircraft design. So this was the kind of thing then that became, if you will, a major challenge in the hypersonics field, was developing very basic data and understanding of what was happening in the hypersonic regime. And just like we had seen the necessity to develop piloted supersonic research test beds in the 1940s and 50s to substitute for the applicability of the wind tunnel to study high-speed flight, where we actually had to use a research airplane carrying 500 pounds of instrumentation and using the sky as a laboratory, so too did we have to do the same thing here with hypersonics. Now, along the way, we had some hiccups. The first of these was Aerospace Plane 1. This was to be a fully reusable vehicle powered by a supersonic combustion ramjet, essentially giving you, through liquid air extraction and collection, giving you essentially single-stage to orbit capability. Unfortunately, although you had some neat, pretty pictures coming out of this, it proved to be an absolute total nightmare. And the Scientific Advisory Board, as you can see in this quote from one of their studies in 1963, pretty much was roundly condemning it in terms of the Air Force investment here. Over-claiming in hypersonics has been one of the problems we've always had. You know, I think we had this later on, if you take a look at the National Aerospace Plane program, the so-called X-30 program a generation later. But this kind of set the stage, if you will, and it masked, in some respects, some of the very important, extremely significant work that was taking place, whether you were looking at reentry bodies or whether you were looking at potentially inhabited air vehicles. Studies such as the Flight Dynamics Laboratory was doing here with people like Al Draper and Chuck Cosenza and Bill Lamar and people like that, and names that are probably known to many of you here in the audience, over that same time period. I mean, there was an extraordinary amount of really capable, solid, rooted work that the Air Force did in that time period, producing configurations that are valid configurations for hypersonics for a variety of unmanned and manned applications, even into the present day. And some of this was reflected in actual flight vehicle development. One of the most interesting programs was the Asset program run by McDonnell, based on work right here at Wright Field by Chuck Cosenza, which was it was an X-20, if you will, after the fact. It was an ability to try to develop the kind of data we lost by losing the X-20 program by developing a flat-bottom, radiatively cooled hypersonic lofted boost glider that we flew over the Eastern Test Range. And, you know, that's not bad. I mean, July 1964, to get Mach 15.5 out of this vehicle and recover it, and you can see it, by the way, in this museum. Charlie has it very nicely exhibited. You know, this is a pretty serious accomplishment. I mean, that's something that I think the Air Force and indeed the nation could take very great pride in. We went beyond that with the SV-5 program, which was probably the most publicized of all the lifting reentry programs of that time period. The SV-5 body shape was a very influential body shape developed by the Martin Company in conjunction with the United States Air Force. And it was the only one that arguably was tested all the way from orbit down to landing. You had the SV-5D, which went from orbital velocity down to the Mach 2 regime, if you will. You had the X-24A, which then took that from the Mach 2 regime, close to the Mach 2 regime, down to landing. So here you had a vehicle that was basically validated the design concept of this vehicle across the entire range of performance, from reentry all through the hypersonic arena down to the transonic, subsonic, flare, and landing. Once again, a vehicle that's within our collection that's well worth seeing. It was also the first to demonstrate hypersonic maneuvering of a lifting body type vehicle during a flight over the Western Test Range out of Vandenberg. So if we take a look at this and we kind of recap and we take a look at where we're coming from in hypersonics and supersonics and put this all together, the dotted line represents the ballistic missile approach that we saw with some test vehicles such as the V-2 in the early days and then the X-17 that I mentioned. We see the progression of supersonic flight with wing technology validators, verifiers, experimental machines such as the X-1, 2, 3, 4, 5, XF-92A. Then we get into the hypersonic region with the X-15, Alpha Draco X-15, and then on up through the Asset program, X-24. We see here, I think, a really remarkable race, if you will, to the upper atmosphere. And the little data point you have there for STS-1 is, of course, the shuttle in April of 1981. One of the most interesting aspects of design thought that we explored in that time period was the joint NASA Air Force lifting body reentry program. There were multiple schools of thought here. You know, I mentioned the X-24A, which you see in the lower left, which was, of course, basically the SV-5 vehicle. NASA had done its own work with studies out of Ames and Langley that gave to us the M2 family and the HL-10 family. When you put these all together with the X-24, and then you took a look at the development by the Flight Dynamics Laboratory of the X-24B, which was basically a gloved X-24A with a tailored, almost X-15-like flat-body hypersonic glider configuration, we had here a vehicle, in the case of the X-24, that actually flew far better than its F-104 chase aircraft. Demonstrating that hypersonics, the manned hypersonic vehicle, the kind of lofted hypersonic vehicle that one could perceive the Air Force ultimately developing for national security needs, was indeed a very real possibility. This led to a program that was called at the time the X-24C. It later led to, that itself spawned what was called the National Hypersonic Flight Research Facility, one of these awkward names, NERF. And unfortunately, sadly, it went nowhere. This was one of these things where we were, I think, a penny wise and a pound foolish. Had this is during the Carter era. Once again, why should we be surprised? But in any case, had money been put, I'm getting short, so I can say that. If we had put money, had we put money toward this venture in that time period, had we put money toward this kind of capability, we might have had a very different and very changed world than the world that we have today. As a result, because we had this flight test shortfall since the time of the SV-5, when we actually developed the shuttle to become the first piloted, inhabited, manned hypersonic vehicle, we find that we were strictly dependent upon laboratory methodologies. We were strictly dependent on what was happening within the shock tube, aeroballistic range, tunnel-type environment for the kind of data we needed. We were not able to get the kind of flight test validation that really would have made us very, very comfortable. Now, fortunately, when we had that first flight, April 1981, by Crippen and Young of STS-1, the shuttle Columbia, things worked okay. But it's not, once again, in retrospect, when you look at this wasn't necessarily the way that we should have been leading our lives in that particular time period. What is often not recognized when you look at the shuttle, and shuttle was very much a design compromise in many, many ways. One of the most interesting aspects of shuttle was given to it by the Air Force. The fact that the shuttle was indeed a winged vehicle, the fact that the shuttle had this very generous delta wing to it, was imposed, if you will, upon NASA by Mike Yaramovich of the United States Air Force. He was Air Force Chief Scientist. We were looking at requirements at that time for using the shuttle to place classified payloads into orbit, in a northerly orbit, coming out of Vandenberg Air Force Base, and then making a hard right, if you will, and coming back to the United States before we re-entered the airspace of the evil empire. And in order to do that, one needed that kind of wing. So really, the payload bay requirements for the shuttle and the shuttle's aerodynamic configuration itself was largely based on Air Force work. Not only that, but the understanding we had of lee side heating requirements on the shuttle, which turned out to be critical to the ability of that vehicle to perform successfully and safely. Once again, that was brought to NASA from the work of the United States Air Force, and that's something that I think has too often been missed. What shuttle did give to us, if you take a look at the idea of shuttle as a space-age DC-3, obviously, in retrospect, it couldn't be that. But what shuttle did give to us was a vision of hypersonics in the future that was at once expansive and perhaps a little bit overblown, but nevertheless it did give to us a feeling for what could be accomplished out there. And so I think, these are really the three areas that we really see some interesting work taking place in. We had the shuttle inspirations that were basically the copycat shuttles, Buran, Hermes, Hope, rapid response systems, Stan Tremaine doing a lot of work here, for example, at Wright Field, working on what became the TAV, or Trans-Atmospheric Vehicle notion, and then some of that work folding into bold new starts, such as the National Aerospace Plane here in the United States, or Britain's HOTOL program, Horizontal Takeoff and Landing, or the German Sänger 2, which was, of course, an ode to Sänger 1, which was the Sänger-bred antipodal aircraft of 1944. We, of course, came up with National Aerospace Plane, the so-called orbital jet, not the most aesthetically pleasing vehicle. The sad thing here, if we take a look at what this vehicle actually gave in terms of capability, we ultimately wound up with a a velocity deficit so that we could not get single stage to orbit with this vehicle. But we were concentrating so much on getting that last percentage of velocity increment to get us into orbit that I think we missed to a very great degree what we had actually achieved with this vehicle. What we had actually achieved here was really a remarkable system that, once again, like the X-20 before it, you think had we perhaps backed off a little bit and had gone ahead with more modest ideas of how we could pursue it, we might have had, I think, a more interesting future. There's been an alphabet soup of programs since that time. You know, this just gives you, I think, a feeling for the various approaches people have taken for a whole range of systems, including some ballistic vertical takeoff and landing systems, DCX, for example, stuff like that, running all the way up to the current X-51 of the present day. The point I would make by looking at all this is that we have the capability, we have a hypersonic future ahead of us. The question is, will we be the ones to actually pursue it? Will it be a two-stage, single-stage, fully reusable vehicle? That's not necessarily the issue. The issue is, are we able to exploit the hypersonic region? Well, here's what the Scientific Advisory Board saw in 1995 when they did their so-called New World Vistas study. They thought that we would have these capabilities by these particular years. Well, you know, in retrospect, largely because of a whole lot of situations that came about in the 1990s, not all of our own doing, think, for example, War on Terror and many other things as well, you know, obviously we are not on track to meet this kind of future. But if you think about the technology and the technology investment area and how we are actually apportioning our resources and where we're doing our work, surprisingly, we're coming to closure in many of these areas. We have the ability to actually pursue these. What we need actually in many ways is the dedication and the vision to stay with one particular vision and one particular future and pursue it to the very end. I'll give you one example. For example, if we take a look at the Why and Withers study that came out by the Scientific Advisory Board in Summer Study 2000, you know, these were pretty encouraging. These were pretty encouraging conclusions. They were also challenging, you know, the idea of developing some sort of concept of operations for hypersonics, the need to develop some sort of ability to have stable funding and support. That's pretty challenging. The need to develop some sort of unified vision of where we should be going in the hypersonics arena. These are things that need to be revisited. They will be revisited. We will look at all these issues. We are looking at all these issues in terms of where we're going with hypersonics. But there is no question that if you take a look at the hypersonics field, that this has tremendous potential to be used for us and, more significantly, to be used against us. It is very, very intriguing to see the investment that is being made in hypersonics research, primarily in weapons research, and the kind of technologies that could be applied to weapons research by potential foes. You know, this is hypersonics is maturing to a point now where it is not beyond the capability of a country, many different countries, in fact, to pursue this and to carry it through to fruition. We have had some important moments here, and I think the X-43 flight was a classic example of this. We did not have a perfect matching of engine and airframe here. We had a supersonic cruise configuration, if you will, with basically an accelerator engine added to it. But if you take a look at the mix, it worked, you know, it worked reasonably well. The sad thing was, after we got our second successful flight off that program, that basically marked the end and was considered the end at the time of NASA's investment in hypersonics. Now, that's once again being revisited as well. But it's very interesting to see that you carry this through all the way to the point of fruition, all the way through to the point of accomplishment, and then you do not choose to go beyond it. The macro view that I would offer to you is that we're in the hypersonics era. You know, if you take a look at where we've been, if you take a look at what we've actually accomplished, you know, we've been in the hypersonic weapon delivery system for quite a long time. It's the old joke that you see inside missile silos where they say, you know, first one delivered in 30 minutes or the next one free. Hypersonic weapons are nearly 50 years old. Hypersonic systems, piloted or not, have already been flying for decades. Think of the X-15. Think of the lifting bodies that I showed you. Think of some of the reentry demonstration systems that we've had. Think of some of the operational systems that we've demonstrated. We have relied on a hypersonic space logistical system now for over 20 years, the space shuttle itself. Over 25 years, in fact, at this point. Where we need to figure where we're going, no matter what future we're looking at, within the national aerospace construct, I think this is where we kind of get a macro view of where we are. Let's take a look at about 3 pictures, okay? In 1976, at the time we opened the Air and Space Museum, this was kind of like a national report card in aeronautics. Now, for those of us who were involved in aeronautics, even on the sidelines in those days, if you cast your mind back, what you see here may not necessarily resonate with what you recall. For those of us who were living the time period, we recall cancellation of the SST, downturn in educational funding and support for aeronautics. We started to see the rise of foreign competitors. We had a downturn in the national attitude towards science and technology. We had the worst effects of a corrosive anti-military feeling coming out of the Vietnam War. There are a lot of things there that were fairly negative. But nevertheless, if you take a look at them in terms of today's environment, it was a veritable golden age. It wasn't as great as what we had in the 1950s, but it was pretty good. It was pretty good. If we take a look at where we were at the 100th anniversary of the Wright brothers just a couple of years ago, I think we see the difference. In the 1950s, in the 1960s, if you flew in the 70s, if you flew a long-range airplane, it was American build. If you flew a regional airplane, it was American build. We were producing up to 18,000 general aviation airplanes a year and selling them all around the world. We were very robust in many of the other areas in supporting science and technology, and even hypersonics had a pretty good future to it. But in 2003, I'll never forget, I was asked to give a talk on America as an aerospace nation, and I got in my Japanese-made automobile, and I drove to my metro center, and I got in my Italian-made rail car, and I went to my airport where I got into my Canadian-built regional jet, and I flew to my hub where I got in my Airbus, and I flew to my destination and talked about us being an aerospace nation. That's an aerospace consuming nation. It's a very different thing. I like to have U.S. on everything I operate. Call me old-fashioned. The point here is that this is the future I think we had in 2003. Not very, very good. And some of this we had done to ourselves. Think of general aviation. We had allowed predatory legal maneuverings and lawsuits to basically destroy a single industry. General aviation was basically destroyed by people out to make a lot of money simply by suing people right and left. Global air transport, well, in some respects we did that to ourselves as well. Regional air transport, hey, if you fly a regional airliner today, it's virtually 100% it's somebody else's airplane. Now, having said this, just over the last couple of years, we've seen some positive changes. I was thinking about this the other day, and in fact, earlier this week I was at the National Business Aircraft Association meeting down in Orlando, and I have to tell you something. I'm very, very encouraged and very impressed by what I'm seeing in what might be called the small company arena. And the thought crossed my mind that we can make direct comparisons to what we saw in aviation in the 20s and 30s. In the 20s and 30s, you had a whole range of companies, some large, some small, all competing to furnish general aviation or mainstream airline aviation or military aviation. And some of these companies lasted, like Douglas, and some of these companies like Thomas Moss, and went by the board. But it was a very vibrant, compelling type of economic environment. And you found that the best people, the qualified people, whatever companies they were with, they tended to wind up having pretty good lives. They may have leapt around a bit, but by and large they had pretty good secure futures because they had skills that were able to carry them forth. I see the same thing today. I think that we're seeing a new industrial model that's going to take us away from this relatively archaic, almost Soviet-style industrial model we have, where you have a fighter bureau and a bomber bureau and a transport bureau and an avionics bureau and a satellite bureau and a space launch bureau. We're getting now down to the point where we're seeing some very small and creative companies that are partnering with other small and creative companies using spin-off technologies, some of which are military-rooted, for example, cruise missile engines, military avionics, military research and structures, military configurations such as fighter configurations that are now being applied to transonic transport designs, and you're finding that this is working very, very effectively. The VLJ movement is one that I would point to, the Very Light Jet movement, which promises to really revolutionize the way we're looking at air transport in this country. This is very, very interesting to see how these things are rooted. Now, I would point out that this is not going to take place necessarily easily. There's some bad news and good news, and the good news itself is not all that great, actually, if we take a look at this slide. This is what I call, and I'm one of these people myself now, this is what I call my geezer slide, okay? If you take a look at where we're going to be putting the national investment in this country, you know, I want to thank you all for paying for my long-term care over the next few years. Thank you very much. And my wife does too. But basically, beyond about 2010, we're going to start having some problems. About 2018, it's going to be very serious. I mean, about 2018, if you're a congressman and you're looking at your next election and somebody comes in and says, hey, I'd like you to buy the whatever aeronautics program, or the choice is putting money in social welfare or social support, you're going to think very hard about where you want to put those dollars because you're going to be very concerned about whether or not you win re-election. Now, the somewhat good news is that everybody's in the same boat. In fact, some are in a far worse boat. You know, if you take a look at the European nations, and this is a compelling argument for capitalism, which I strongly believe in. If you take a look at the European nations, they have socialized themselves out of existence. They have developed such a materialist, non-value-based, socialist, nanny-state view of the world that they have destroyed their ability to compete. And they have destroyed their initiative. We certainly see this with the Islamicization of Europe. And we see this certainly in the way that their industry functions, in the way that their societies function, and so that actually they're in even worse shape. But this is a problem that we need to address. This is something we need to get around. And that's why I think it's very encouraging to see these small companies, because these small companies are operating with lower overhead and lower built-in expenses into their operation. And therefore, I think there is some hope for us continuing to make this second century of flight the kind of century of flight that we had the first time around. This is an interesting little chart if you think about it. It's that 660-600 mobility chart that I mentioned earlier, and then I decided to kind of update it and run it out to about 6,000 miles per hour, the turn of the next century. Now, obviously, you can see where my sympathies lie. Not surprising given the fact that my private email is drhypersonic@aol.com. And by the way, if any of you wish to communicate with me, feel free to do so. But anyway, you know, I find this kind of a compelling chart. It tells me that we have a hypersonic future. The only problem I worry about is it our future or is it somebody else? Is this going to be the great trans-Asian hypersonic consortium or the great trans-European hypersonic consortium or what? You know, I'd kind of like to see this rooted in the United States. Once again, call me old-fashioned, but here I am. The point I'd like to conclude with is we had a commission a few years ago that was undertaken by Congressman Robert Walker and by Whit Peters. It was a bipartisan Republican Democrat study of the aerospace industry, and they concluded that, as I said, the time for action is now. That was back in 2002. We're beyond the point where the time for action is now. General Michael Mosley said just a few days ago at the dedication of the Air Force Memorial, America soars in Air Force wings. You bet it. That's absolutely true, a true fact. If you take a look at the history of the United States, if you take a look at the history of our investment in flight, it's rooted in what the Air Force did. I would like to imagine that 100 years from now, we'll have another historian who will be talking about the last century of flight and the developments of the accomplishments that were made in the 21st century as we turn into the 22nd. And I hope he's standing right here in this museum. But it's up to us to make sure that takes place. Thanks very much.